So chemical bonding has a lot to do with what's going on with the electrons. And so this is going to be our first introduction to Lewis structures. And we use Lewis structures to represent how the electrons are arranged in molecules, and it tells us about the chemical bonding. And this is going to be an important topic for the next several lesson plans and indeed the next several chapters. And so this is going to be our first introduction to these Lewis structures. So another term for Lewis structures is electron dot structures. And so when we draw Lewis structures, we use the symbol of the element to represent the nucleus and all of the core electrons. And then we put dots around the elemental symbol to represent the valence electrons. Now I do this a little bit differently than the book describes it. So the way I do Lewis structures for atoms is I use the four sides. If you imagine putting a box around the elemental symbol, I use those four sides to represent the top, the outermost s electrons, and the outermost p electrons would be on the other three sides. And so we use a dot to represent each electron. If you think about oxygen, its electron configuration is 1s2, 2s2, 2p4, where the 1s electrons are core, and then it has 6 valence electrons. It has 2 in the 2s and 4 in the 2p's. And so if I was drawing the Lewis structure for oxygen, I would put 2 dots on the top to represent the 2s electrons. And then, just like when we do orbital energy diagrams, and we put 1 electron in each degenerate orbital before any orbital gets 2 electrons, I do the same thing when I'm drawing the Lewis dot structures. And so for the 4 2p electrons, I have 1, 2, 3, and then the 4th one gets paired up. And so that's how I would draw the Lewis structure for an oxygen atom. A carbon atom has 4 valence electrons, right? It's 1s2, 2s2, 2p2, right? The 1s2 is core, so I don't represent those in the Lewis structure, but then I would put 2 dots for the 2s, and then it has the 2 2p electrons. For sulfur, it has normally 6 valence electrons. In the case of S2 minus, it would have 8 valence electrons because it's picked up those 2 electrons. That's why it has the -2 charge. And so for sulfur, you don't have to write out the Lewis structures each time. I'm just going to do it so we can kind of see what's happening. The electron configuration would be 1s2, 2s2, 2p6, 3s2. Normally sulfur would be 3p4, but because it's -2, it's 3p6. Right, so these are all the core electrons. I don't have to draw them. But it has the 2 in the 2s, and then it has 1, 2, 3, 4, 5, 6. And then when we have ions, what we usually do is put the whole thing in brackets and then put the charge in the upper right hand corner. And so that would be the Lewis structure for S2 minus. Alright, so the next thing I want to talk about is the Octet Rule. Now this is something that we've alluded to a number of times over the course of last semester, but here we're going to introduce it a little bit more formally. So at least for main group elements, so things in the S and the P block, when they bond, they tend to gain, lose, or share electrons to result in 8 valence electrons. Right, that's where the octet comes from, 8 octet. Right, so basically they want to have 8 valence electrons, or have an ns2 np6 configuration, right, where n is just whatever the valence shell is. And so we've kind of talked before about how atoms like to look like noble gases, and that's because noble gases have these 8 valence electrons. Now there are a lot of exceptions. Hydrogen, lithium, beryllium, and boron, the closest noble gas to them is helium, and so they tend to adopt electron configurations like helium, so we might call that a duet as opposed to an octet. We'll also see as we go on that elements in the third period or below, they have empty d orbitals that we can put electrons into, so they can often exceed the octet rule at times, and we'll revisit that later. And then when I first mentioned the octet rule, I said this largely applies to main groups, so the S and the P block. Transition metals, and for that matter, lanthanides and actinides, they don't obey the octet rule. But for a lot of compounds that we're going to look at, the octet rule is very important and useful. Alright, so we want to finish off this video by talking about drawing Lewis structures or Lewis symbols for ionic compounds. Now they're pretty easy. At least the ones that we're going to start out by drawing only involve monatomic ions. And so all you have to do to draw the Lewis structure of an ionic compound is to draw the Lewis structure of the ions that are present. We have to get the ratio of the ions correct so that the charges cancel out to be zero, but we'll see how to do that. So let's look at a couple examples. So first, let's draw the Lewis structure for the ionic compound formed between sodium and sulfur. Alright, so we need to know the formula, right? So we need to know the charges on a sodium ion and a sulfur ion. So sodium is here in the first column. It's a metal, so it's going to want to lose electrons. So we have Na+. Sulfur is 2 away from being a noble gas, and so sulfur likes to have a -2 charge. And then in order for this compound to be neutral, I need to have 2 sodiums for every 1 sulfur. So the formula of the compound is going to be Na2S. And so when I draw the Lewis structure, I want to draw the Lewis structure for an Na+. And so sodium normally has 1 valence electron. So if it becomes +1, then a sodium ion has 0 valence electrons. So the Lewis structure is just going to be Na. And since there are no electrons or anything else, we wouldn't put it in brackets. And then we just did S2- in a previous example. So S2- is going to look like that. And then to get the ratio correct, what we do is when we draw the Lewis structures is we put the number in front of the ions. So it would be 2 sodium ions and then that sulfide ion. And so this would be the Lewis structure for the ionic compound formed between sodium and sulfur. Let's do one more example like this. Alright, so now I want to do aluminum and oxygen. So aluminum is right here. Again, a metal, it's going to want to lose electrons. We know that aluminum is one of the ones that reliably forms 3+ ions. Oxygen's right here, the same column as sulfur. It likes to form, oops, sorry, not sulfur. Oxygen likes to form 2-. So the formula of this compound, in order for the charges to cancel, is going to be Al2O3. And so aluminum normally has 1, 2, 3 valence electrons, but it forms a +3 ion to get rid of its valence electrons. And so the Lewis structure for an aluminum ion would just be Al3+. O2-, oxygen normally has 6 valence electrons. When it's -2, it now has 8, so it's completed the octet. So I can just put the 8 electrons around the oxygen. Indicate the charge. And then I need to put the number of ions in front. So we have 2 aluminum ions and 3 oxygen ions. And so this would be the Lewis structure for aluminum oxide.